Hi, I'm sqrt and I wanted to share some of my favorite math problems with you today. These are a couple of quirky little problems from the NYSMATYC contest, which is a competition between two-year colleges, so basically community colleges in upstate New York. The whole exam is about an hour and you don't have a calculator. You can complete as many problems as you feel like and you get points for them, but you also get negative points for the ones you messed up. So really no one answers all the questions, they just answer the few that they feel confident on. These aren't necessarily ones I would have answered, but they're also not necessarily the hardest questions. They're just a few that I thought were pretty fun and that I wanted to share with y'all. So let's dive in. This first one's from the spring 2013 exam. It's problem number 2, and it's really cool because of the recursiveness of how it works. There's a bunch of problems that show up like this over the years, and most of them you have to solve by marking something within the fraction itself as the original thing and then having a finite problem to solve.
So here's the expression we want to find the value of. After this, the 3 and 6 just keep repeating infinitely. Let's set it equal to x. If we add 3 to both sides, we can perfect the pattern alternating right from the start. Now what can we do? Well, we see that this thing inside is really just x plus 3 again, so let's sub it in as x plus 3. Now we have a finite expression that we can solve, so let's do that. Let's start by multiplying that one denominator up to each of the terms to get this. So we can continue simplifying this, multiply by x plus 3, remove the common factors, then we can FOIL it out. There will be some like terms that we can simplify, and we eventually get to x equal to square root of 11, which is answer C.
This is from that same exam. It's problem number 11, and as you can see, it's a little themed with the current events of the day.
Every number from 0 to 9 has one and only one letter representing it, so let's just write out each of those numbers so we can mark them when they're assigned. Given two starting conditions, I equals 0 and n equals 4. Now we can rewrite the equation with those values subbed in. I'm going to use the little dash through the zeros to make sure we can tell them apart from O's. Oh, whoops, that's a 0. Now we notice that W must be a 1 because no matter how large these numbers are, they can only carry over a 1. Now for m plus e to equal e, m must either be a 0 or it must be a 9 and a 1 has been carried over. We know that 0 is already claimed, therefore m equals 9. Now for that 1 to be carried over, a has to be great enough that a plus 4 is greater than 10. So a equals 6, 7, or 8. Those are our options. If a equals 6, then r equals 0, which is already taken. A equals 8 is okay. If a equals 7, r equals 1, which is also already taken. Therefore, a has to equal 8. So now let's rewrite this out again. Oh, whoops, keep messing them up. Now we have r equals 2, and there's just a few options left for what e could be. Now we must be having to carry a 1 over here. We can solve this column. 8 plus 1 plus d equals 4, so d must equal 5, so e isn't 5. Options, but let's look at this leftmost column. B plus O must equal 10. There's only one set of options remaining that can equal 10. Regardless of which one is which, this gives us only one option for E.
Again, in that same exam, this is problem number 8, and it's asking how many trailing zeros you can get in 2013 Factorial. He does this a bunch where he uses the year itself that the exam was in. Obviously, we don't want to compute 2013 Factorial, so we need a simpler way to do this.
And that simpler way is going to be using the fact that all trailing zeros are the result of a factor of 10, or in other words, a factor of 2 paired with a factor of 5. Because there are way more factors of 2 in 2013 Factorial, we only need to count the number of factors of 5 that are present. So how many factors of 5 are there in 2013 Factorial? Well, there's 1 per every multiple of 5 that's less than 2013. So how many of those are there? Well, the greatest multiple of 5 under that is 2010, so we divide that by 5 and get 402 multiples of 5. Then we get an additional 1 per every multiple of 25, so greatest multiple will take 2000, and 2000 divided by 25 gives us another 80 multiples of 25. So then plus 1 per every multiple of 125. Same idea. We can just divide this by 5 since it's still going to be 2,000 is the greatest one. Gives us 16. And add 1 for every multiple of 625. So that gives us, let's just count them, 625, 1250, 1875, and then the next one would be 2500, which is too big, so we only have 3 of those. So we have 402 plus 80 plus 16 plus 3 multiples of 5, which adds up to 501 multiples of 5, and equivalently 501 trailing zeros. Aren't you glad we did not calculate that by hand?
And then number 19 in this exam might look kind of familiar to you. The handshake problem gets used a lot in popular math, but this is a little bit different in that you have couples. Still, it's very, very much the same.
So let's review how this problem works if it were just singles.
I always like drawing out the triangle itself. It's more satisfying to me that way.
Model this as just 6 people. So the first person would shake 5 hands, the next person 4, 3, 2. The second to last person would only have 1 hand to shake, and the last person would have already shaken everyone's hand. For n guests, we appear to have a triangle with sides n-1 and n-1. Number of handshakes should just be the area of the triangle, which is 1/2 n-1 times n-1, right? Well, not quite. The reason we have 1/2 base times height is because a triangle is a half of a rectangle. But let's see what happens when we draw the full rectangle for this one. See that to make the triangles match each other, one side of the rectangle actually has to be n and not n-1. This makes the triangle's area n times n-1 over 2. Now let's see how it works in the couples version. If the number of couples is n, then we now have 2n guests, and they're all shaking the hands of all but 2 of the guests, themselves and their spouse. So if there were 264 handshakes, we can figure out how many couples were involved. Let's multiply out this expression and divide by 2. We can factor and get n-12 times n plus 11 equal to 0. We know that the number of couples has to be positive, so there are therefore 12 couples attending.
Okay, let's move on to some more recent problems. This is from fall 2019, which at the moment is the most recent exam that's been released. There wasn't a spring 2020 exam because of coronavirus, which was unfortunate. But so here is question 3 from fall 2019. And it's a lot simpler than it looks once you get into it.
We have this expression and we want to know the set of numbers it can equal. Well, we can simplify that a little bit by using this identity, which I'm sure you're familiar with. 1 minus sine squared just becomes cosine squared, and vice versa over here. It might look like we have the same thing on the top and bottom of both fractions, which would just go to 1 plus 1 equals 2, but it's really more complicated than that, because since we're taking the positive square root, you have absolute value on the top. Now each of the fractions can either be positive or negative 1, and therefore your options for a solution could be plus 1 to 2, or plus and minus getting you 0, or minus and minus giving you negative 2. There's 3 options.
Problem 10 from this exam has been used, I think, another time in almost the same form. The other time it was a cone with a sphere inside of it. So here's just the 2-dimensional version.
So here's your figure. The semicircle is tangent to the triangle both on the left and where it meets the hypotenuse. We have side lengths 2 and 5, and we're trying to solve for the radius of the semicircle. What can we do? We know that this is a right-angled triangle, and we also know that the radius always meets the outside of the circle at a right angle. We also know that we can divide the base of this triangle into r on the left, and therefore 5 minus r on the right. Now, because these two right-angled triangles share the same angle, we know that they must be similar. As similar triangles, they should have the same ratios, so for both of them, hypotenuse divided by the shorter side should be the same. Multiply by 5 minus r, FOIL it, group r's together, and divide by their coefficient. And finally, we can simplify this by FOILing out the denominator. And there you have it. We don't have a calculator, so there's no need to simplify that any further.
And then let's do one more problem before we run out of time. This is number 13 from that same exam. There's usually at least one problem that deals with natural logs, so this is it.
So here's our triangle with sides ln4, ln3, and lnx, and we're trying to find all the possible integer values for x. So how? Well, there's two different cases. First, we can assume that lnx is not the longest side, in which case ln4 is. And with some log rules and a little bit of algebra, we can see that x has to be at least 4/3. Note that this is when x is not the longest, so this is the smallest possible value of x ever. The other case would be when lnx is the longest side, in which case the other two sides have to add up to being larger than it. Again, we can do a little bit of algebra, and we see that x has to be less than 12. So, with values of x between 4/3 and 12, x can equal 2, 3, 4, anything up to 11, which is a total of 10 separate values.
So that's all we have time for today, but I will be back really soon with part 2 of this. In the meantime, you can go to the NYSMATYC website and look up old exams to try some of these problems for yourself. You can also hit the subscribe button and the bell next to it so you'll be notified as soon as part 2 comes out. Hope to see you then. Bye.